are quite late. Yeah, we didn't record that at the beginning. Yeah, I keep in this recording so that so later, suppose you needed to use this to build in your model, so that will help. Okay, I starting from this part. Okay, we say here, we given that in the motor property. So the motor property. So firstly, we given that in the motor property for the work cooling of the model. So work cooling model, we have three of the parameters. So the cohesion, the friction angle, and the tension strength. Yeah, according to the principle of the FDEM, so we have the fail only along of the a cohesive element. So then in that case, for us to given that property, we only needed to given that the cohesive element. And for the triangle element, actually you do not need to give. So we regard the triangle element as the elastic. Yes, so I have another of the PhD student is working on that. Yeah, since elastic, so that's not so realistic. So we plan to make that electroplastic. So then that's the failure, which is still a follow that's the cohesive element. Okay, we specify that's the cohesion, so that's 5 megapascal. Okay, so then that's the friction angle is 25 degrees, tangent 25 degrees, so which is equal to 0.4, and so on. So then we specify that's the tension strength. Okay, the tension strength, sorry, I have this one, actually should be correspond to this one. So tension strength, which should be 1.77 megapascal. So then besides that, you notice that we have here have a homogeneous index. Yeah, if you are familiar with the RFPA, so then you are familiar with the homogeneous index. Yeah, so here, this is that we follow what is that in RFPA. We using that in the web of the distribution. Okay, if you given this value like this, I given this value, which is an extremely big of that value, then in that case, which means, yes, I have a number of that's the cohesive element, or that's the triangle element that's here. So if I given this value, which is quite big, that means all of this the cohesive element are given that in the value, which is the same as this one. Yeah, I can use that I specify this that like that in RFPA, we put in this that's M, we put in M equal to 2. Then in that case, when you given that in the tension of the strength or that's given a cohesion, so you will have a wide ranging of that in the distribution. So then you given that on heterogeneity. Yeah, so if we say that's central, this one, which is equal to 5 of megapascal. If we given that a very big of that value, that means everywhere. So you given that value, which is equal to 5 megapascal. But if you have that taking this value, which is small, you will have a range of that the distribution. Okay, this is exactly the same as that following that in the RFP of the concept. Okay, so this is that's the input parameter, the strength input parameter. Okay, then the next one, the next of that parameter, so which is the fracture of the energy. Okay, we have the constitutive model is like this. So initially, so we approaching to peak, then we have that, if we have the tensor, so that's the strength softening, which are approaching to the bottom. So if we have that in the model 2 of that failure, so then you will have that not to the bottom, since you will have here, that's the current of the friction. Okay, so for this one, you will have an energy release, okay, which is this one for the model 1 of the fracture. We require you to input of this value of that here. Okay, the integration of that the loss of the energy. So that's the value of that here for the model 2. Okay, so for the model 2, the releasing the energy, so which is this part. Okay, in RFPA, actually, we regarding this as that's the acoustic emission. Okay, so we require you to input this parameter. For this parameter, actually, so we do not have the guideline, how we calculated that, especially for the model 2, G2. Yeah, ourselves, we do not have that in the guideline how to calculate that. At this moment, we have that in the input parameter, actually, we use the try and error. Okay, for the G1, you may use this formula to calculate that. So what is the corresponding of the input in here? So we know according to that the elastic mechanics or the fluctuation mechanics. So you have that in this of the formula, E, that's the elastic modulus, V, that's the Poisson's ratio, K1C, that's the model 1 of the fractal toughness. Yeah, so elastic modulus and the Poisson's ratio, that's usually, for most of the rock, we can get into that. And for the KRC, the model 1 of the fractal toughness, you do not usually to get in that. Then in that case, you can use that in empirical of that formula. So the empirical formula, so that's the unitary, since this empirical is not theoretical formula, so actually the dimension so is not consistent with each other. You need to use this dimension. So KRC, so then the unitary is megapascal, and then this root of that, the M, equal to 0.145. The tension strength, so suppose for that rock, you know that's the tension strength, then you can give this value. But for the model 2, yeah, so there is no this kind of formula that's available. So what I need to automate that at this moment, this input parameter, so you need to choose that based on that the experience. Okay, so this is that in the fracture energy. So besides that, the next group of that in the input parameter, okay, is that in the viscous of the damping. Yeah, we say for HFDEM actually, so that's using the explicit finite element method. So what consider that's the dynamic problem to turn that the dynamic problem to the quasi-static or the static problem. So you need to use that the damping. Okay, so here that's the critical of that damping. Okay, how we calculated that the damping is using this formula. Okay, if you know, so E, that's the elastic modulus. P, that's the density of the rock. So H, okay, so this is the average of the length of the elementary size. Yeah, so especially for the case if you're using that unstructured maze, non-uniform maze, so it's difficult for you to determine what is that in the H here. Okay, actually, so our program will automatically to calculate this, what is that the viscous damping, as long as they control parameter, you ask the program automatically to calculate that. If you're using the non-uniform of the basis, so you need to check in that, letting the program automatically to calculate the viscous damping. If you're using that uniform of the base, you can directly to using this formula. Then you calculated the crystal boundary number it's put in here. So this is what is the meaning of this in the viscous damping. Okay, the remaining of that's the parameter here. So that's the lambda constants, and that's the okay. So that's the lambda. Yeah, so that's the U or that's the shear of the modulus. So then that's the elastic modulus. Then that's the penalty. So all of that which is related to the elastic modulus of the Poisson's ratio. Okay, I think that's for the most of the rockets, it's easy for you to determine what is that's in the elastic modulus or that's in the Poisson's ratio. So after you know the elastic modulus of Poisson's ratio, we can, according to the elastic mechanics, to calculate what is the lambda constants. Okay, lambda constants lambda. So according to the elastic, we have this formula. Yeah, so the elastic modulus multiple the person's ratio divided by one other person's ratio, then multiple 1 minus 2 times of the person's ratio. Then you can calculate the lambda. Okay, so this lambda, so that's what is the input parameter, which is we using that here. Okay, so for this problem, I think that we have that elastic modulus, so which is 12.2 of that's the gigapascal. So then the Poisson's ratio, so which is 0.25 or 0.3. Okay, if you use this substitute into this formula, so you should have given that and getting this and that's lambda, which is equal to this one. Okay, I think that's this is equal to 0.3. Then for the U, okay, this is the secondary Labe constants. Okay, so this is actually which is this one, or that's the shear modulus. So you using this formula, you calculated that, so you were given that in the input parameter. So that's given that in here. Okay, then the remaining, that's in the homogeneity index. So that's the same of the concept. Yeah, so with what we introduced before, and the same of the construction in our RFPA. So what is that's the M of that's the value of the here. Okay, so then the remaining here, so which is giving a contact. So we know like that's the loading plate and the rock sample, which is contacted with each other. When contacted, you must allow some of the penetration. Okay, so what we do is that, so we making this the contact of the penalty. So we making this which is 10 times of the elastic modulus. Okay, like this one. So we say elastic modulus, which is 12.2 of gigapascal. Okay, so that's E multiple, so 9, multiple 9. Okay, multiple 10. Okay, oh, sorry, I have here actually is the 100, but actually, according to our parametric analysis, you have that's 10 times of E, so that's sufficient. Yeah, it's unnecessary for you to use that in 100 of that E. Yeah, I previously show you one of my PhD students did a parametric analysis, actually, which is using 10 times of E, so that's sufficient for that's the contact of the penalty. Okay, so this is considered that's the contact. So besides that, you notice here, so we have that's the cohesive element. So you will have a cohesive element penalty. So that's could consider. So we say, if we do not have an element to fail, but we still have that in the cohesive element, which is inserted that's between of the triangle element. For you to insert the cohesive element, if you do not fail, you need to make sure this represents the continuous behavior. So our guideline is you have here, which is the 100 times of that's the E elastic modulus. Then in that case, so won't it affect your results significantly? Okay, so this is that's the parameter for Labe constants and that's the values of the penalty. Okay, so let me clean my computer screen. Then the next one. Okay, so you notice that the parameter we can give that the okay, sorry, I skipped another. I needed to go back into the previous screen. Okay, so we given that the damping. Okay, for two objects, like we dropping a ball. Yeah, if we have dropping a basketball to the ground, yeah, so if you lift that and which were reference to back into the initial of that in the head, yeah, but if you dropping that in another kind of a ball, yeah, like that, yeah, handball, when you drop that, it won't be able to come back into the initial of the head. That's because that you have the loss of the energy. So for the contact, to modern that we using that in the damping. Actually, we implemented two types of the damping. So one of that damping we using this exploration of that equation, and another of that we follow that what in the discrete element code like the particle, the PFC particle flow of that in the code. Yeah, so they implemented that in the damping. Okay, so here in the control parameter, you can control, so whether this is that's in the damping, you are using that or not, or you do not. Yeah, actually for the uniaxial compressive test, yeah, so for the plate and the rock, yeah, that one, so we can ignore that's the contact of the damping. You can, yeah, it's unnecessary for you to use this one. In the control parameter, you can control whether this will use. Okay, suppose if you do that out of the body, you need to use that. So the concept of what we introduced here is that, so when we have that in the contact, so we follow this line. So you can see here, this is that linear of that line. When we have that the detach, so then we follow this line. So you will see this have a loss of that energy. Okay, we using a simple of that's an example. For example, here I drew a ball. Here that's an elastic of ball. So I have that the initial of the velocity, which is 10 meters, which is hitting. So here a wall, this is a triangle of that in the wall. But adjusting this and that's the parameter, that's t, and that's p, and that's the b of that the parameters here. Okay, the physical meaning of this parameter b, that's a power of that here. Yeah, that's t, so that's the value of that here. Okay, yeah, so then p, so that's they consider their contact of that the penalty. Given that the different value, so you can see if you given that b equal to 1, you do not given a cutoff t, you have the cutoff setting that's a maximum, and then you have that the p penalty, which is equal to 0.1. Then in that case, you do not have any of the energy loss. Then you adjust that parameter, so you will see that's the energy loss there. Okay, anyway, so this represented the contact damping, although for the uniaxial compressive test, you do not need this for your uniaxial compressive test. Okay, so then the remaining of that's the parameter, so that's the friction of the coefficient. Okay, so this one is different from that's the Bohr cooling. So we say for the Bohr cooling, what are we given that's the a friction angle, which is given that for the cohesive element. So this one, which is given that, suppose after we have the cohesive element, which is fair. So what is this residual of that the friction of that the surface? So the triangle element, so after you have that the cohesive element fail, so then, yeah, what are we representing? Well, we're using that in the rock mechanics, which is called the residual of the friction of the coefficient. So this is still that's tangent of that the phi. Yeah, so usually, so this value we will have that, which will be smaller than that the cohesive element. Okay, so then after that's the density, then that's given a homogeneous of that's the index. So that's the same of that value of that's the m. Okay, the remaining, so that's the boundary condition. So we have introduced before. So I will not introduce, so this is the boundary condition. Okay, so this is that and all of that the input parameter. Okay, after that, so then you will have this that's this is that's the boundary condition. We already explained this in the previous one. So after that, so then you have the complexity of that the model. So that's ready. Okay, then you will have this 2 input file. Okay, so let me stop into. So then you will have that the input file. Okay, so you will have this that's 2 input file that's ready. So what today we focus on to explain that, which is explains this part. This part I put in that into the PowerPoint presentation. So this is that how do you give that input parameter? Okay, so then the boundary condition, so that's we already introduced that this one at this moment you do not need this one. So this part actually is when you do the grain-based modeling, so you need to use this one. So that one I will introduce that later. Okay, so then we have that. Then we copy this to exe file. I have already done that. So I have that. Okay, I have already done that. Then I run this. Okay, so then which we're getting that in the results in here. Okay, the results that's what is that in here. Okay, then we do that in the calculation. So then you will see that's in the final of that in the failure. Okay, so this is that's the calculation of the results. Okay, I will replicate this results in Tencent's computer. So after that, today of the presentation, I will copy that into input file, and that's simple of the C++ of the input file to Tencent the computer, then replicate this buttons there. Okay, so let's briefly look at that. You will see that's the stress. Okay, so let me go into early of the stage. Yeah, so during this stage, so you do not have any of that failure occurs there. So you see that's where the stress is building up. So then after that, okay, we goes into that's 150. So that's already, okay, so we starting from 100 steps, yeah, show that's in the animation. Yeah, so since this is two-dimensional modeling, so part of view, we're easy to show that's in the animation. Yeah, you can see that's in the formation of that's in the crack. Yeah, then after that's in the crack, which is forming, so we still have that's in the current of the friction. So then you will see that's in the current of the friction, which is causing the shear of the band. Yeah, okay. Yeah, so then here that's in the last of the step. Okay, so after that, so you will have that in the input of the file. Okay, let me go back into the PowerPoint of the presentation. Okay, you can have show that in the results in the parallel view, and you will draw that in the stress strain curve. Depends on how do you choose that in the parameter, especially how do you choose that in the after the failure of the friction. So if you given a relative or bigger of that in the tenure of the file, so you will see this the strain of that in softening. Otherwise, you will see that in the previous one, which is yeah suddenly, which is dropping that into to the bottom. Yeah, okay. So I stopping here. That's today. Yeah, so for the corresponding of the file, I will share that to you. I will copy them to Tencent's computer. Yeah, okay, so I handed this back to you.
Okay, thanks for your presentation. So the next is question time. If you have any question, we can ask Professor Liu.
Yeah, I'm demonstrating this as a series of that USC. That's in the early part when the data structure, actually, which is the same as the previously for the two-dimensional of the BTS test. Yeah, I'm really hoping through this demonstration of the series of the lecture, so the students will be able to construct their model themselves. Yeah, from the scratch. Yeah, starting from the obstacles to do the geometric modeling. Yeah, obviously for the obstacles, I didn't introduce how to use the obstacles, but obstacles, so that's the commercial of the software anyway.
Yes.
Yeah, so that's has very good of that in the tutorial, which is available in the internet and in the obstacles of that in the website. Yeah, hopefully that's in the future. Yeah, after a series of the lectures, the student will be able to build the model from the scratch and they to using our software. Yeah, I think
Yeah,
that
yeah,
yeah, it should be that's easy. Yeah, for the students to use this software, yeah, to assist with their own of the research. Yeah, so I think that's yeah, so many of the students in our group, you were more or less to use the numeric modeling. Yeah, like in
yes,
thinking, I noticed that when you're looking on things the computer, it seems the things is learning on that the machine learning. Yeah, so using that the pattern to using the machine's learning to process the data from the macroseismicity. I think that for the macroseismicity, yeah, you can using that in the software to model. So what is the mechanism, yeah, causing that in the macroseismicity? I think that we previously have many of the examples using the RFPA to model that in the macroseismicity. Yeah, we can do that in similar here, yeah, to using the HFDEM software to model that
yes,
in the macroseismicity, yeah, to assist them with yeah, I wanted to say, so that's the year 4 of the part of your thesis, which is working on the numeric modeling. Yeah, usually I think that's in China, yeah, especially for good of the PhD thesis, you need to have that in, yeah, the laboratory test. Yeah, so then the numeric modeling, then the field of that in the observation, that's a perfect of that in the PhD thesis.
yeah, yes, yes. Okay, any question? I have some question, Professor Liu.
Yeah, great. Yes.
The one is about the Brazilian test. I found the value of the simple initial to boundary of the loading boundary, but as we know that the initial value of the Brazilian test is at the center of the simple. So
Yeah,
this
so ideally, if we have that in a homogeneous of that in the sample, so we
yeah,
should have that in the crack, which were exactly initiated from the central. But for the case, what we are modeling here is that using the unstructured information, which were causing more or less that's in the
yes,
heterogeneity.
yes,
Right. Yeah, actually, so we did that and we can prove that. Yeah, so let me share my computer screen again. Yeah, so to demonstrate this concept. Yeah, so we did that into construction on completely the structure of that in the mesh. Okay, so let me show you that in one of that in the publication. Yeah, so for this one, if we construct that in the completely structured mesh, we will be able to have that in, yeah, like in this one, you will see that in the crack, which is exactly initial that
yeah.
it is the center of the sample. Yeah, I think that's is related to that's in the heterogeneity, yeah, introduced by the unstructured meshes.
Okay, thanks. Other question is about the uniaxial compressive test. So I found that the shear crack is the crack pattern is shear crack dominant, yes, which is very similar to the laboratory findings. So, but as we know that another typical value is a splitting value. So because when I model this task, this tag in RPA, I found that it is difficult to model the splitting value, even
Yeah.
though we use the tensor criterions in RPA, but most of the results are dominated by the shear value. So
Mm-hmm.
has similar finding can be also found in dynamic compressive test.
Yeah.
So Yeah, I had this question. So have you ever got the splitting failure in your from your software?
Yeah, so for the uniaxial compressive test, so let me share my computing screen again. So actually, you will notice that for our case, the majority of that's the failure. So which will be that's the mixed mode of that failure. Okay, so let me clean the so looking at the failure of the mechanisms that's in here. Yeah, so we have here, we will be able to show that's in the mixed mode and that's in the failure mechanism, or that's in the pure mode 1 failure mechanism, or that's in the pure mode 2. Yeah, so actually you notice that in here. So we have very few. Yeah, so okay, let me put in these scales over here, so that's more clear. Yeah, so USC have that very few of that in the pure mode 2, and very few of that in the pure mode 1 of the as well. The majority of that in you will notice that yeah, so that's the mixed mode of that in the failure. Yeah, I think here this is that related to the definition, how we have that in the pure of that in the tension, or that's in the pure of that's in the shear. Since for our case, we have this and that in the meshes, so we have here. Yeah, so if let me show that in the meshes. So you will see here, we have this. Yeah, actually, you will see this that's the unstructured meshes. Yeah, on structured basis, although we have the loading, we have that in the vertical direction. Actually, so it should be easy to present that in the splitting of that in the failure. But corresponding each of that in the local of the location. Yeah, so like that, if we look at that in this element, so we have that in the loading, so that's in this direction, so that's in this direction. But we have that the fair, actually, which is an inclined plane. So it will be exactly, so you will have that in the pure of that in the tension, or the pure of that shear. For each of the case, you will have more or less of that in the shear, or more or less of that in the tension. I think that's yeah. I mentioned that I think that for our case, we have here that's the definition of the problem. Yeah, so we have that's the damage at this moment, which is defined like this. Okay, here we have that's the damage of that tension, and here that's the damage of that the shearing. Yeah, only in this case, we regard that as the tension and the shear. But for the both the case, we look at that the majority of that, so actually which were located inside of this region. And for this region, we regard that as the mixed model. So which explains why we have here. So majority, we have that's failure, which is the mixed model. Yeah, I think that yeah, we can change the definition. Yeah, like that we have the cohesive element. Yeah, so the cohesive element, so we have here that's a few of that the integration of the point. Yeah, I think that's at this moment we've using 4 of the integrations part. We need to all of these 4 of the integrations part, which is have that's in the pure of the tension failure, then we define this as the tension failure. Similarly, for the shear failure, we need to all of these 4 of that's in the integrations point, which is failed in the shear of that model. Yeah, I think that's in the we were modified in this. Yeah, for the since we know the pure of the tension and pure of the shear, which is difficult to occur. Yeah, I think that we can define that as known as one of the integrations of the point, which is the tensions failure. So then we can define this is as pure of that tension, or one of that as the shear. Then we define that as the pure of the shear. Maybe that will be improving. Yeah, we will be able to better model that. Uh, like that in the experimental observation, I think that in most of the experimental observations that for the uniaxial compressive test, so you should have that in the failure mechanism, the observation of the failure mechanism should be that's the tension of that failure. Yeah, instead of that's the shear failure, is that what you mentioned, that's the splitting of that failure. Yeah, I think that's this is related to the differently software, how they exactly to define that's the tension failure or shear failure or mixed burden of the failure.
Okay, thanks.
Yeah, obviously for our software, so we have that. I think that we already noticed that we have the limitations about the definition. We plan, yeah, to modify that's the criteria, yeah, to improve the failure mechanism presentations as well.
Yeah, okay, thanks. So another question, would you please show your screen again? Please.
Yes.
It is the last page of your PowerPoint.
Yeah, the pump handle presentation. Yeah, the last page.
Yeah,
Yeah, they.
the last
Yeah.
page. Yes, this is force and loading time curve. So so is I from the load the scale of time is 1,000 microsecond. So from the view of dynamics, have you considered wave propagation from the loading area because it's the time is considered in your modeling?
Yeah. So as we said, so for uniaxial compressive test, actually, so this is a static problem. But actually, so HFDEM or FDEM, this is using the explicit finite element method. So actually, which is treating this as a dynamic of the problem. Yeah, for the dynamic problem, what we do is that using called that's the strain of the relaxation, which is using the critical of the damping. Yeah, making that becomes a static of the problem. Yeah, so you were noting that for the modeling, so you can see that yeah, so if we look at that in this the stress of the distribution, so you can see that they initially where have that the propagation of that the stress. Okay, so let me show that on the surface. So let me show this that's the vertical stress. So from that the initial. Okay, that's the scale. Okay, so let me make this scale becomes bigger. So you will see that the initial of this, that's the stress of the building of the process. Yeah, actually, so initially, which is corresponding. Okay, let me further adjust the scale. Then let me play this video again. So you will see that initially, yeah, so that's the stress building of the process. Yes, but here we have demonstrated here this widely have a bigger of the influence. Okay, so the loading rate, yeah, so obviously, so here this that's the loading time. Let me share that in the screen. So this is that's in the time. We have that in the loading rate. Okay, let's go into the pump handle presentation. Goes into the, okay, we have that in the loading rate. Okay, loading rate actually is which is 0.05. So we using the time multiple. Okay, so yeah, so let's using that in the product. Okay, so we have that in the time multiple 0.005. So then that will be the loading displacement. So then you can calculate that. So what is that the loading displacement? Yeah, here that's yeah, rocket so is quite big. So that's the loading of the displacement. So that's quite small, representing the typical of the breach of that failure. Yeah, so can give that the evidence. So while we say we have the loading rate does not have a bigger of that the influence. Okay, so here we model that's a test using the differently of the loading rate. Yeah, so here, so that's using the differential of the loading rate. Yeah, so you can see from that's 0.02. Yeah, so we cannot use very high of the loading rate. So for example, if you using the loading rate 1 meter per second, so then in that case, which is the dynamic effect, so which will be quite obvious. Yeah, but if we using that in the loading rate, yeah, so which is quite small, so like that, yeah, so 0.02. Yeah, so then in that case, which is correspond to that's called static. So you have that in the loading rate, increased loading rate do have that in the influence, which will make that more looks like the dynamic. But if we have that in the loading rate, which is control that's small, so you will have that in the influence that's small, which will close to the static, or that's in the quasi-static of the loading of the conditions. Yeah, it's true for us to model that the static problem, we mostly making sure the loading rate, so which is quite small.
Thank you. I have the last question. The last question is not about the semi today. So is about dynamic modeling. Yes, you know that I did some dynamic modeling before. But when I consider this consider the bursting or impact loading, the log or the other specimen commonly under the state of the state loading. For example, the initial stress. So when I model this program, we commonly the coupled static and dynamic loading must be considered. So when I model this problem using RPA, I first did the static loading and I need to save the NVM result, for example, the displacement result of the static analyzed, and then I model the dynamic loading. I can also obtain the displacement result. So before the damage and analyzed, I need to multiply the static result and the dynamic result, and then we calculate the stress and deformation information before to do the damage analyzed. So what is considered in your software to model the coupled static and dynamic loading?
Yeah, so I didn't quite get in the question. So do you mean is that the input parameter for the static of the modeling or dynamic modeling?
How can you consider the coupled static and dynamic analyzed?
Yeah, so the different input parameter of this the static test and the dynamic test. Yeah, obviously. Yeah, so for the dynamic modeling, is for the strings. Yeah, we needed to consider that the increase of the strings, since according to the experimental test, so the dynamic of the strings, so which will be higher than that in the static strings. Or let me use that. Yeah, one of that our paper as an example. So like in this one, so we have this paper which is initially building the static of the uniaxial compressive test and the pre-distance test. So then after that, we build in a dynamic of the, we build in that in one of that SHPB of the test. Yeah, for us to determine of this parameter. Yeah, so this parameter is according to Molassen's results. Yeah, according to their experiment of the result. Yeah, for us to determine of the elastic modulus. So we actually they provide us that the elastic modulus for the static of the test, but for the dynamic test, so they are unable to model that, giving us that the dynamic elastic modulus. So what we do is that we based on their stress wave propagation. So we based on their stress wave propagation, then we determine of that the input parameter. Okay, so let me, so list find that in the table of the input parameter. Yeah, so we should have a table which will show that in the input parameter. Okay, so for the dynamic test, we should have a table which is similar to this one as well. Okay, yeah, so sorry for this one. I don't think we have that in this a table of that input parameter. Yeah, so but
the parameter of the simple in static analysis is different.
yeah,
from that
exactly.
in dynamic analysis.
Yeah, it's
Okay.
different from that the static of the test. Yeah, I think that's the strength. Yeah, the strength which is much higher compared with the static. Okay, so we have that around here. Yeah, then the yeah, so input a parameter. Yeah, so we determine the dynamic. Yeah, so if we reading that from here, yeah, we based on the Bayesian. Okay, so let me change it as a color. Yeah, based on the Bayesian's density and the dilation of waves, velocity. So we given that the dynamic, determine that the dynamic, Young's modulus. Yeah, so then the remaining. Okay, so let's continue to that's on the next page. So if we given that exactly the strength of that in the parameter. Yeah, so yeah, okay. Mm-hmm. Yeah, sorry. So this one we didn't give that the exactly of the input parameter. Yeah, but I confirm. Yeah, so that's the input for parameter for the dynamic of the modeling. Yeah, is different from that for the static of the modeling.
Okay, I got it. Thank you.
Yeah, great.
And other questions?
Okay, so let me stop the recording.